Since the introduction of the 3D flash memory, the prevailing paradigm in the industry has been to shrink the die size by stacking layers, which is the vertical shrink, and by lateral shrink. But over the past few generations, it has weighted heavily more on stacking layers, which resulted in a CAPEX-intensive structure. This graph shows that CAPEX related to stacking layers and forming memory holes have an upward trend over the BiCS flash generation. It shows that stacking more layers results in higher CAPEX intensity. This trend is observed across the entire 3D flash memory industry. Considering the significant CAPEX associated with the layer counts, it is important to effectively increase the gigabyte density by finding the optimal balance between the vertical shrink and lateral shrink while reducing the amount of CAPEX. Let's take a look at our BiCS Flash Gen 8, which is in mass production. Compared to the previous generation, we have gained 26% in density from vertical shrink, 24% from both CBA and lateral shrink. Spending less CAPEX and with less number of layers compared to the industry's 230-layer generation products, it achieved the highest gigabyte density. Let's look at one of the lateral shrink technologies we implemented in BiCS Flash Gen 8, which is CBA, CMOS directly bonded to array. CBA is a technology that enables to process the CMOS and cell array wafers separately and bonding them face-to-face. This technology enables minimizing the overhead area required for signal routing area, achieving lateral shrink. Also, from the performance and cell reliability standpoint, since the CMOS and the cell array are processed independently, optimal thermal process can be applied to each wafer. This results in improved performance and cell reliability. The BiCS Flash Gen 8 1TB TLC, which is in mass production, offers the following: 3.6 Gbps interface speed, random access speed of 35 microseconds, over 200 megabyte per second write performance, and over 1.5 gigabyte per watt write power efficiency. While maintaining the optimal CAPEX efficiency, these best-in-class performance were achieved. I like to say that this is the technology leadership, and we are receiving many positive feedbacks from our customers. We are also sampling the 2TB QLC, which is the highest capacity QLC die available in the market today using the same BiCS Flash Gen 8 technology. By stacking 16 dies, we can achieve 4 TB in a JEDEC standard package and 128 TB SSD by placing 32 packages onto the PCB. We are also working on stacking 32 dies to enable even higher capacity SSDs. Lastly, let me talk about KIOXIA's future migration plan, the dual-pronged migration strategy. KIOXIA will leverage the CBA technology and combine it with the existing stacking technology to increase the gigabyte density and address the performance requirements for small capacity dies. This approach enables us to offer high-performance NAND with minimized CAPEX. Also, we will continue to develop the cutting-edge technology by stacking more layers just like before. CAPEX will be focused more on products capable of achieving huge leaps in gigabyte output, such as large capacity QLC. KIOXIA will make the most effective use of CAPEX and blend the two migration paths to deliver more gigabyte and the performance necessary for a wide variety of applications.